Um, all right. So what we did last time is we finished off the harmonic oscillator. And so our next topic is the free particle. And so our starting point for the free particle is just the time-independent Schrodinger equation, except that for a free particle, the potential is everywhere zero. If you think about it, we've seen something like this. If we think back to the infinite square well, um, what we had is zero potential inside the well, and then it went to infinity outside. So we'll come back and think about that and maybe connect these two pictures, the infinite square well and the free particle, at some point during this class. Um, but what I'd like to do is to start here and see what kind of progress we could make in trying to determine the stationary states that we get from solving the time-independent Schrodinger equation. Okay, so I'll just make the point that if we were to collect some constants, let's say we were to multiply by 2m and divide by h bar squared, we would have this 2me over h bar squared. I'm going to define that in terms of some other constant k, and actually I'm going to make k the square root of all of that, 2me divided by h bar. So if we do that, if we define this k as, or sorry, just define k as this, then we could rewrite our time-independent Schrodinger equation as two derivatives of psi with respect to x is minus k squared times psi of x. Okay, and so this is the thing we're going to solve. Before we do that, let's just interpret what the meaning of k is. So for a free particle where the potential is zero, its only energy can be kinetic energy. And kinetic energy is p squared over 2m is one way to express the kinetic energy. And for a free particle with like matter waves, you just think back to physics 200, momentum was like this h bar over k. And so I'm going to write this as actually let's do it like this. K is p over h bar, and p is related to these things by 2 pi over lambda is the wave number. So that's what k is physically representing, is the momentum divided by h bar, which corresponds to like this 2 pi over lambda. So that's our interpretation of k. K is a wave number. So it's kind of analogous to angular frequency being 2 pi times frequency. Our wave number is 2 pi. This time it's divided by lambda. All right. So we've seen something like this before. This is just like inside the infinite square well. And so, in fact, the way we solved this problem in class is we assumed solutions of the form psi of x was going to be a e to the I kx plus b e to the minus I kx. So this is a solution. You can see that it's a solution because if I take one derivative, I'm going to get an ik down or a minus ik. If I take a second derivative, I'm going to get I squared k squared. And over here, the minus signs will cancel. I'll still get I squared k squared. The I squared is going to give me my minus factor here. And the k squared is going to come from here. So it is indeed a good solution. All right. So then what we know from separation of variables is that I can stick the time dependence in and say, well, okay, these stationary states would evolve with time as psi of x, which we just wrote down. And then we had this time evolution was governed by e to the minus I times the energy times t divided by h bar. Okay, so if I put that in, we would say, well, that gives us psi of xt is going to be a e to the I. Okay, so for the position dependence, it's just going to be kx, either plus or minus. So we're going to get a kx. And then we have to put in our minus iet over h bar. And so let's think of e t over h bar. What is e? E is going to be k squared h bar squared over 2m. K squared h bar squared over 2m. And then we have to do t divided by h bar. And so there it is. We can cancel a factor of h bar. And what we get inside our exponential is k squared h bar t over 2m. So that's what we have to add here. So let's put that in. So we'll get a minus h bar, minus k squared. Actually, okay, h bar k squared over 2m times t. And then we got plus b times e to the I. Now, the only difference is we're going to pick up a sign in front of this k. So it's going to be a minus kx. So I'll put the sign out front here, minus I kx. And then what I'll do is I'll make this a plus. So this will be plus h bar k squared over 2m times t. Okay, and so that's what our solution is with the time dependence incorporated. The interpretation of these is that this first term represents a wave that's traveling along positive x. The way you can think of it is we know these are just like oscillations. It's like sine, cos plus I times sine. So if I allow time to evolve further, my argument's getting more negative. So to offset that, I have to let x grow if I want to keep my point fixed. And so if letting x grow corresponds to propagating along positive x. On the other hand here, if I let time evolve, I'm shifting, I'm making this more negative. But if k, if we go in the negative x direction, that would correspond to offsetting the growth here. So this is a forward traveling wave, and this is a negative traveling wave. So this is forward traveling wave. Okay, and this one with the negative sign in front of our k is a backwards traveling wave. In the next section, what we'll end up looking at are particles scattering off of potentials. And so we could get reflections off of some kind of potential. And that's where we're really going to have our backwards traveling waves come and be important. So we'll send in something incident to the right. If something comes back to the left, there must have been a reflection of something. And so that's what we have coming in the next couple of sections. Okay, so in these expressions, we've used that E is h bar squared k squared over 2m, which, remember, h bar k is just the momentum. So this is just p squared over 2m. What's different between this current case and the case of the infinite square well was that from here, what we did is we started to enforce our boundary conditions for the infinite square well. And in that case, we had to have our wave function vanish where the potential went to infinity. And enforcing those boundary conditions restricted the values of k that were allowed. We would have to have half integer multiples of the wavelength fitting inside of our well. So in the infinite square well, the boundary conditions restricted the allowed values of k. And this led to quantization. Once k was quantized, because the energy is equal to h bar squared k squared over 2m, the energy of our particle is also quantized. What's different now is that I'm not in a well. I don't have boundaries where the potential goes to infinity. And so there are no conditions that restrict the value of k. So k is a continuous variable in this case. So here, with no boundary conditions, k is continuous, and there is no quantization. All right, fair enough. What Griffiths does next is he says, well, these two look similar. If I just reverse the sign of k, those two terms seem quite similar. And so he's going to relax the condition that k is positive, and we're going to allow k to go negative or positive. Whereas when we did the infinite square well, we said k was like n pi over a, where a is the width of the well. And we chose only positive values of n, which meant we only dealt with positive k. Okay, so we're going to allow k to be positive or negative, in which case we write, so I'll write it as psi sub k. I'll put some new coefficient d, and I'm going to write this as eikx minus h bar k squared over 2m d. And I'll try to do a little justification why this form is equivalent to the one at the top. Okay. First thing I'll say is if k is positive, it's like the term on the left. If k happens to be negative, it's like the term on the right. So let's go through this little argument now. And let's just emphasize here, k is equal to plus or minus square root 2me over h bar. Yeah.
So this new case, it can cover when A is non-zero and B is zero, or when A is zero, B is non-zero, but like both the left and right way couldn't exist at the same time for this new equation.
Right. So let's go through this argument. If we consider, let's take k to be some positive value, okay, for this first case. We'll do the negative one as well. So I'm going to say to enforce k is positive, I'm just going to set it equal to plus k naught, where k naught is some positive constant. Okay, so if I want these two expressions to be equivalent, I want them to be equal to each other. So what we're going to require is that d, evaluate at k0 is some positive number, times e to the I k0x. So all I'm going to worry about is this first part of the exponential. I don't care about the second part because it's k squared. Whether it's positive or negative makes no difference. So I'm going to force d e to the I k naught x to be equal to the sum of these two terms, where I'm going to ignore the time dependence because it doesn't matter. Okay, so this must be equal to A at whatever k naught is, e to the I k naught x, plus b e to the minus I k naught x. And so if I compare these two, like, it's obvious that I have only a positive exponential on both sides. And so here, therefore, for all k greater than 0, D must be equal to A and B is equal to 0. Okay. So if we take the other case, so we're going to take K to be negative, with K equal to minus K naught and K naught some positive constant. And then we'll just do the same thing. So we put in minus K naught. And so we'll have e to the minus I K naught x. So we need that to be equal to A K naught e to the I K naught x plus B K naught e to the minus I K naught x. All right. So now I have only a negative exponential on the left. And so for K negative, we would take D equal to B. I can be more explicit. This one is a little like this. And A is equal to 0. So we'll be consistent as long as we enforce this. When we have negative K, our D coefficient is equal to whatever B was. When we have positive K, our D coefficient is equal to whatever A was. All right. So that should work. Yeah.
Why is it A as K naught instead of like A as negative K naught in that second one?
Because in that first form, K had to be positive.
Right.
Yeah. Yeah.
And then, sorry, one other question. So this case, this like simplification can only work if one of A or B is 0, right? Like if both A and B are not 0, then this new one doesn't work.
I'm not so sure about that because I could have a solution here where we have you know, a forward going and a backward wave. Yeah, let me think about that. And
yeah, like I just don't know how you'd express it with the D.
Yeah. Right. So, but the D, this case, we could consider the D case, we could consider K's that go positive and negative, right? But you're saying not at the same time.
Not at the same time.
Yeah.
Like this D case couldn't represent a solution where we had a forward and backwards translated.
Right. But so let me, I think I agree. Yes. Okay. So, what I want to do then is emphasize that even with all of that, we have a problem. And so here's the problem. I'm going to take this psi of k xt, and I'm going to claim that it's not normalizable. And it's going to be pretty easy to show that that's the case. So let's consider taking psi, and we'll take the absolute square. So we'll take psi and multiply it by its complex conjugate. In fact, right here, actually, I should put my subscript k to be consistent. So I need a k in here as well. Okay. But if we go look back, we have an exponential with an I out front. So when we take the complex conjugate, we just get that exact same exponential with a negative sign here, so that when we multiply psi with its conjugate, that exponential cancels exactly, and it leaves only the absolute value of d squared. Okay. But our normalization requires the following. So normalization requires that the integral of psi squared has to be equal to 1. But we just said psi squared is some constant. That constant can come outside the integral. And it's not possible to satisfy this condition. This integral here diverges, And so we can't pick a D other than 0, which would satisfy this normalization requirement. And so what we've come to determine is that these are not actually allowed stationary states for the free particle. Okay, so what we'll say is this diverges. We cannot find D other than 0.
Well, if D is 0, wouldn't that also not meet the condition? Because
Yeah, if D 0, then there's just no wave function. There's no
that
particle.
also doesn't.
Yeah, that can satisfy normalization. And so therefore, what we have to do is we have to say that psi k of xt is not a satisfactory stationary state. And in fact, there are no free particle stationary states. What I like to think about is the infinite square well. For the infinite square well, we found the stationary states at finite energy. And those stationary states were just like a sine of kx kind of thing, where k was restricted. But inside the well, all we had was oscillations, just regular sinusoidal oscillations that get cut off at the boundaries of the well. So how could you make a truly free particle? You could think of taking a well of size A and just making A bigger and bigger and bigger and bigger. So then the boundaries get further and further apart. As you do this, the K is still quantized, but the spacing between neighboring Ks gets closer and closer and closer together. And so what happens is you could have sharp, finer and finer oscillations, higher and higher frequencies. Nevertheless, for a stationary state, it's just a pure sine wave until you reach those boundaries. And so now if you make A go to infinity, you still have a pure sine wave that oscillates over all space. And of course, that never goes to 0. And that's why you can't normalize it. Okay. So, yeah.
And the case in which like psi isn't psi of k, like for the two contradictory ways, does the same argument still apply because they're both still infinite plane waves, so they still can't normalize?
Yep.
Yeah.
So, having said all of that, we know the psi k's are not these stationary states like we had for the infinite square well and the harmonic oscillator. We would still like to write our wave functions as a superposition of these states. So we would still like to write solutions to the full time dependent Schrodinger equation as linear combinations of our separable solutions. And the way that I propose to do it is the following. Let's take the full time-dependent Schrodinger equation solution, and I'm going to write it in the following way. So we're going to sum over k. And so now k is going to be positive and negative. And then we're going to have some coefficients. I'm going to index them by k. These are like our Cn coefficients, but I'm going to leave a space. I'm going to add something in there in a second. And we'll take our psi k solutions here. So this would work in principle, but as we increase think of increasing the well size, making it bigger and bigger and bigger, k is no longer a discrete variable. It can have any value. It's a continuous function. So as I add more and more CKs that are more closely spaced together, I'm adding more and more terms into the sum. But we also had this other restriction. Remember, the CKs when we did the infinite square well, we would have said something like, if I took the sum of CK and squared it and added them all up, they'd have to equal 1, because each of these told us the probability of finding a particle in a particular stationary state. If I did that for K continuous, then I'm going to have more and more and more of these, and they're all positive numbers. So I can't add up an infinite number of these and expect to get 1. So the solution is to say, well, let's scale our CKs by delta K. So if I had a narrow infinite square well where there's big spacing between our K states, then this is some big number. And so I scale my coefficients by this. But as I widen the well, I decrease the spacing between allowed states. I get more and more of these, but I'm just going to scale each of these terms by this decreasing delta K, and that's going to preserve this sum. And eventually, we're going to go to the limit where A is infinite. This becomes infinitesimal, and so we have this continuous sum where we preserve this normalization requirement. So that's the idea. So let's call this Cn, and we'll make a comment. So as we add more and more terms to the sum, we compensate by shrinking each term's contribution. So that is, we're going to scale by the delta K spacing. Okay. So in the limit that K is continuous, our delta K goes to 0, and this sum over K of delta K is going to go to the integral over a continuous variable. And CK is going to go to not just a coefficient of a single stationary state, but some continuous function of K. It's going to be a continuous function of K. I'm going to call it phi of K just to match Griffith's notation. So then what we end up with is, let's see, we'll say our full solution to the time dependent Schrodinger equation is going to look like, well, our sum is going to become an integral. So we're going to integrate over K from minus infinity to infinity, and I'll put in a dk over here. Our Cn, we're going to write as, we already have the delta K, we're going to write the Cn as this function of K. And then we're just going to put in our station, well, what we're hoping we're going to be stationary states, but we've shown aren't allowed. But we'll write those in, h bar k squared over 2md, like so. So that's exactly what we had. There is one other little prefactor by convention. They put in a 1 over root 2 pi here. So this is by convention. But it doesn't really matter too much, because remember, the CNs are going to be something that we are going to force to normalize. And so if we're going to have some normalization of this, we could pull out or add in whatever constant we want. It'll be taken care of by normalization. All right. So what we have then is this beast that we want to interpret. Okay, so here are phi k along with the prefactor 1 over root 2 pi. Whoops, 1 over root 2 pi. And the dk, this plays the role of the CNs. But the sum is a continuous integral now. Okay, so this psi of xt is called a wave packet, and I would guess that you've probably seen some kind of version of a wave packet in Physics 200. I'm going to try to show you kind of my version of this argument in just a second. And it consists of a continuous distribution of k values. The weighting of these different traveling waves is determined by the shape of phi of k. So in order to remain a finite wave function, phi of k must go to 0 at very large k's, positive and negative, and then it could have some kind of whatever shape you like in the middle, and it's going to tell you how much of a traveling wave with a particular value of k contributes to your wave function. So that's the idea. So the question is then, well, suppose we were given an initial state by x of 0. And we're asked to find phi of k such that psi x of t is equal to psi x of 0 when t equals 0. So we did this kind of thing. We did this for the infinite square well. We also did it for the harmonic oscillator. So we're kind of wrote down a general solution. We said, okay, here's some particular initial state. What are the CNs that give us that initial state? What CNs do we have to pick to match our general solution to the initial state? So how are we going to do that for this wave function? Okay, and so that's the first little job that we have. Okay, so let's first, I'm going to do this different than Griffiths. It's not better or worse, it's just a different approach. So we're first going to multiply by e to the minus I k0x, where k0 is just some constant. It's not related to the k0 I used before. It's just some constant. And after we multiply by this factor, we're going to integrate with respect to x. Okay, so we want the integral of psi of x0. This was our given initial state. We're going to multiply it by this exponential factor, and then I said I was going to integrate with respect to x. Okay, so that's the left-hand side. On the right-hand side, well, what do we have? We have a 1 over root 2 pi. We already have an integral. That integral is over k. I might give myself a little more space here. That integral is over k. Okay, and then we had a phi of k. And then we had an e to the I kx. Think? Yeah. All right. Okay, so this is at, I'm going to do this at t0. So I'm not going to write down the h bar k squared over 2m times t. All right. So what I don't have yet is I don't have my integral over x. I didn't add that in, and I haven't multiplied by this factor. So I'm going to do that now. So we'll do the multiplication. I'll put that over here, e to the minus I k 0 times x. I can take this inside of the k integral because I don't have a function of k. K0 is just some number, it's a constant. So I can bring it inside. Likewise, I can integrate in either order. So I'm going to choose to integrate with respect to x first. And so I'll put in my red integral with my red dx. All right, good. So that's what I wanted, I think. So let's see where this takes us. So these two things, I haven't changed anything at all. And so we'll write this as integral from minus infinity to plus infinity, e to the I, and then we'll do k minus k0 times x dx. And I'll put some brackets around here. And then I still need my dk. All right. Does anybody recognize this thing in blue brackets? Have you done the Dirac delta function? I heard people talking about EM. Have you done the Dirac delta function in E and M?
Yes. Yeah.
So it's like the divergence. One way to represent a Dirac delta function is the divergence of like r hat over r squared, that kind of thing.
Yeah.
Right. So this is another representation of a delta function. And I'm going to try to convince you, it's not going to be necessarily a rigorous proof, but I'm going to do a demonstration, I hope, that this is equivalent to 2 pi delta k minus k naught, the Dirac delta function. Okay, so let me just finish off this calculation, assuming that this is true. And then once we're done this little calculation, I'll try to justify this. All right, so assuming this is true, what are we going to get? The 2 pi is going to partially cancel with the 1 over root 2 pi. So we get root 2 pi, integral from minus infinity to infinity, phi of k. And then we have, well, it's delta k minus k naught dk. But delta functions are beautiful things. Just like the Kronecker delta kills sums for us, the Dirac delta function kills integrals for us. What's the value of this integral?
By k0.
Yeah. So this is just equal to phi evaluated at k0. All right. And let's bring down, we still have the left-hand side of our equation. I'm not going to do anything to that. So this is going to be e to the minus I k0 x dx. Now, this result holds for any k0. I put in a constant, but I could have chosen that constant to be anything. So this is valid for all k0. And so therefore, we would have the integral from minus infinity to infinity of phi of x0 e to the minus, this is valid for any k, so I'm just going to write it as k is equal to 5k. All right.
You lost your square root of 2 pi.
I lost my square root. Yes, that's true. You're right. I have to divide by root 2 pi. Exactly. Thank you for that. 1 over root 2 pi. So what I want to do is I want to compare this result, which let's think about what this result is doing. I'm putting a function of x into this integral. I'm multiplying by some exponential factor, and then I'm integrating over x. Once I integrate over x, all the x dependence is gone, right? Really, we're just calculating the area under the function of phi times the exponential. And so that just returns some number that's independent of x in the end. But it will depend on k. Okay, so if I change k, I'll get different answers when I evaluate the integral. So we put in a function of x, we evaluate the integral, and we get a function of k returned. Now let's go back over here. And here we have the opposite. I have a function of k I stick into an integral. We can forget about the time dependence for this discussion. So I multiply by some exponential, I integrate over k, and what's left is a function of x. And so we have this way of transforming from functions of x, which is like position in real space, to functions of k, which is going to be like our momentum. So we can move between thinking about things in terms of position or in terms of momentum, and momentum is like inverse wavelength. And we could go either way. So we can get a function of x out, or we can get a function of momentum out. These tools are not specific to quantum mechanics. It's a general principle, and they're called Fourier transforms. So in general, if we had some function of x, it could be expressed as this integral of a function of k. So this is called the inverse Fourier transform. And we can go the other way. And it's nice that these are such symmetric expressions. So we're going to have in here a function of x. And the only thing that changes is the sign in front of the exponential, the argument of the exponential, and the fact that we change the integration variable. And so this is the Fourier transform. And what I'd like to do is I'd like to first justify this step where we replaced this with the delta function. And then I would like to look at some properties of these Fourier relationships. If you are reading the textbook, when Griffiths does this, I think it's problem 219, but I could have the number wrong. But he gets you to, starting from here, essentially go to here, following a bunch of steps that he outlines. If you've taken physics 331, or you're taking it now, that's something we do exactly. So if you're in the course now, we're going to do that in a week or two. Yeah.
Your capital F of K is actually an F of X, right?
Oh, yep. Yep. Okay. Yes, good. Perfect. All right, good. So let's try to go back and let's try to justify this delta function relationship that I used. So let's return to, it was e to the I k minus k naught times x integrated with respect to x. And I claimed that that was 2 pi times this delta function, delta of k minus k naught. Let's justify. So I won't say derive. Let's justify this expression or demonstrate that it works. Okay, so how are we going to do it? What I'm going to do is I'm going to evaluate this integral for not the limits minus infinity to plus infinity. I'll evaluate it between, say, some minus L and plus L. And then that will allow us to do the integral. And then I can take, in the end, the limit that L gets really big. Or I could at least, if I can't do that analytically, I can at least look at what happens when we take L large. So let's consider the exact integral that we have. I'm just going to change the limits. This is nice because this is easy to evaluate. We get a 1 over I k minus k naught e to the I k minus k naught times x. And then we go between minus L and plus L. All right. So that's, I'm going to do it this way. I'm going to put a 2 here, k minus k naught. And then I need a 2 and an I. Okay, so these 2's cancel. I have the I k minus k naught in there. So now I just have to put the limits into this exponential. So this is e to the I k minus k naught times L minus e to the minus I k minus k naught times L. So I picked up the minus sign here from the minus L in this limit. All right. What is this thing under the above the red brace?
The sum.
It's the sine. That's right. This is sine of k minus k naught times L. And so what we have is 2 sine k minus k naught over times L divide by k minus k naught. And so this is something like the sinc function. If you've seen the sinc function like sine of x over x, it's not exactly the same because I don't have an L here, but it's sinc-like. This is like a sinc function. And so what I claim is that this goes to 2 pi times a delta function as L goes to infinity. And so I'd like to try to show you that that happens. And I'm going to show you here. Let's see if this works. Okay, so can I get rid of this thing? Let's move this somewhere else. Okay, so what I've got here is a spreadsheet. Here's my K0, and here's my L. So right now I have K0 set to 1/2, and I have L equals 1. So L is not infinity right now, it's just equal to 1. And then I'm calculating a bunch of kx values. I'm going to go from minus 1/2 to plus 1/2. I chose that range just because it puts our k naught in the center of the screen. If we think that this function is going to give us a delta function, then it should peak at k naught, and it should be a very narrow, very sharp peak. Okay, and then this column that's labeled y, that is exactly 2 times sine of k minus k naught times L divided by k minus k naught. It's the thing that we want to be equal to 2 pi times the delta function. The last column is the integral of the function. So it's a running total of how much area is under the function from minus 1/2 to 1.5. And there's 1 million data points in here. I used 1 million data points so that the integral returns a value that is quite accurate. But the problem is when I do that, the calculations take a long time. So every time I change a number, we'll have to wait for this thing to update a bit. But let's do it anyways. What's the integral of, if I had a delta of x and I integrated over all x, what do I get? 1. Okay, so if I'm going to claim that our function y is 2 pi times the delta function, then I want the integral of that function to be 2 pi times 1. I want to get 2 pi, 6.28. And you can see here at the end of our integral, all the way out when we get to here, we're nowhere near 2 pi. So this is definitely not a delta function right now. However, it is kind of peaky at the right point. So we'll at least give it that. So what I'm going to do is I'm going to change the value of L. I'm going to make L equal to 10. Okay, so I'm going to make it quite a bit bigger. So it's saying, oh, you've got to do some calculations. So it's claiming that's going to take 15 seconds. All right, so there it's updated this plot. What I'm going to do is I'm going to rescale the plot so that we can see what it looks like. So we'll let it do its millions of calculations. It has to do a million calculations to get the new k values, the new y values, and the new integral. Okay, so it's updated. And well, it's still near our k naught value, and it's a little more narrow. Okay, it still has these funny little side lobes, but it's getting to be more sharply peaked. If we look at the integral, it's 6.6, so it actually overshot. It's above 2 pi. Okay, so what I'm going to do is I'm going to make a bigger change. So I'm going to go to 1,000 for the size of our well. Right, so I made the width of our well 1,000 times bigger than it originally was. And so we'll wait for these updates to happen. Okay, look at that. So now when I make my well bigger, I get tighter and tighter oscillations. It's gone way off the screen, so I have to rescale this. And we'll give it a second to do that. And I also want to see our integral. All right, and so now this is getting very sharply peaked at k naught. There's very little weight outside of that, and it's very sharply spiked. However, even though the spike is very high, up above 2,000, the area is now 6.28. And so you're probably already close to convinced. I'm going to do one more here. I'll go to 100,000. So now we got a massive length. We'll let that update. And let's see what happens. And this will be the last one I do. So it still has to calculate the new y values. Hopefully it's thinking about it. There it goes. All right. And so now you can see that our delta function is essentially zero width, infinitely high. It's way up at 200,000. Nevertheless, the integral, I hope, is still 2 pi. And there it is, 6.28. Okay, so that's a demonstration of this delta function equivalence of that function we were looking at. And so let me go back to this screen. So, oh. Let's see if we can make this happen. Oh, I think I probably have to stop the main one first. Okay. All right, I think we're back in business here. All right, perfect. Okay, so it worked out. So yes, the integral from minus infinity to infinity of e to the I k minus k0 times x dx is equal to delta, in fact, there's 2 pi delta k minus k naught. So this is the kind of a useful identity actually to have in the back of your mind because it crops up every once in a while. Okay, good. So I want to see if we can understand what these wave packets are actually doing. So let's interpret the so-called wave packets. And we're going to do it by considering the infinite square well, a problem that we've already solved. Okay, so our infinite square well had stationary states that were given by, it was 2 over square root of a was our normalization factor. And then we had sine of knx, where kn was n pi over a. And the energy is h bar squared kn squared over 2m, which is the same as n squared pi squared, h bar squared divided by 2ma squared. Okay, so that's what we know about the infinite square well. Let's just draw the potential. I'll use the potential that Griffiths used, where he went from 0 to a, and here below x equals 0, the potential goes to infinity. So this goes to infinity as well. This goes to infinity. V goes to infinity. And in here, we get V0. So that was the geometry. So the first thing that I want to think about is the spacing of the k-states. So note the spacing of k-states. So what I mean by that is if I was to look at the difference between the kn+1 value and the kn value, well, that's just going to be, what is it, n+1 times pi. n+1 times pi over a is kn+1 minus n pi over a. So we'll cancel here and cancel here, and all we're left with is pi over a. So the real important point that I want to make is as we increase a, the difference in k neighboring k values gets closer and closer and closer. And in fact, that's the trick. When a goes to infinity, that difference goes to 0 and k becomes a continuous variable. So this is a delta k. So as the width a of the well is increased, the spacing between allowed k values delta k is pi over a decreases. Okay, so fair enough. So with that in mind, what I want to do is think about a superposition of neighboring k-states. So we're going to consider a superposition of infinite square well stationary states. The reason that I want to think about this superposition is because that's exactly what we found for our free particle. It was a continuous superposition, but it was still a superposition of different modes of k. So let's see what that looks like for the infinite square well. We're going to say, let's take some initial state. I don't care about the time dependence for this argument. And all we're going to do is sum over the allowed n values. In fact, I guess something like this, Cn sine n. Okay, and what we'll do is we'll pick Cn. Those Cn's will follow some Gaussian distribution. So it'll be peaked at some n, and then it will tail off from there with some width. And so if we go to really small n or really large n, we'll be at the tails of our Gaussian. And so those aren't contributing much. It's only the stuff near the peak of our Gaussian distribution that's going to matter. So we're going to take Cn as being drawn from a Gaussian distribution. Okay, so a Gaussian distribution is something like, there's a 1 over root 2 pi sigma prefactor, and then it's e to the minus 1/2. Then what I'm going to do is I'm going to pick some mean for k, and my Cn's are going to be determined on how close we are to that mean value. And then I will set some width. I guess I put a k subscript on my width, so I'll put k subscript there. And so my kn is going to be n pi over a, and my k bar is going to be some n bar pi over a. So n bar could be 5 or 6 or 100 or whatever, something like that. And so what I'm going to do is I'm going to start with sigma k, the width of our distribution, much smaller than the spacing of our states. So if you think of what that means, then I've got something like allowed k values. So these are allowed k values, something like, boom, there's some spacing, right? So these are the allowed values are marked by these red vertical lines, and the spacing between them is delta k. And I'm going to choose my Gaussian distribution so that it's narrow compared to the spacing. And so this would be like some sharply peaked Gaussian, something like this. And so this is my Cn's are drawn from this distribution. So there would be one here, there'd be one here, and here, and here. But all those ones are going to be 0. And so we're only going to have one state really contributing initially. And then what we'll do is we'll relax that restriction. We'll allow more and more states to contribute. The way we're going to do it, just to let you know, is I'm going to take A of the infinite square well, I'm going to make it bigger. As I make A bigger, the spacing is going to decrease. So if I keep increasing A, eventually these states are going to get tighter and tighter together, and we're going to get multiple states sitting inside our Gaussian envelope, and we'll start adding more and more of these stationary states together. And I want to see, what does the resulting wave function look like? Okay, so as we increase A, the well width, delta k shrinks, and more k-states, more allowed k-states fall. Oh, what happened there? I didn't do anything. Screen sharing ended. Okay. All right, so more k-states fall within the Gaussian distribution. Okay, so example, I'm going to take H bar equal A equal M equal 1 initially. And delta K in this case is pi over A. But if we take A equals 1, it's just pi. So that's the spacing of our K states, is just pi 3.14. To make sure that our sigma K is narrow compared to pi, I'm going to take sigma K equal to 1/2. And I'm going to take N bar equal to 5, which means K bar is N pi over A. But A is 1. Nope. Dentist. All right. So that's what we've got. Then what we'll do is slowly increase A above 1 such that delta K decreases. Okay, so what we'll do is I've got another program for showing you how this will work. Okay, this one is linked on the course website. And so let's just go through this quickly. The first thing I'm going to do is I'm going to define a function that just generates exactly the stationary states. So square root of n over 2 over a sine of knx. All right, so that's fine. And then we'll define a Gaussian distribution. This will be used to help generate our Cn values. And so there's the Gaussian distribution, minus 1/2 k minus k bar over sigma k all squared. And so here are the actual Cn values. We just pulled something from the Gaussian. This thing is just used to shift my wave packet to the center of the well. So it's just a technical detail. Whoops. So shift enter. All right. And here is a function we're actually going to build the wave functions. The important part is here. The wave function psi is Cn times the stationary states, and this plus equals just means that we're iterating a sum. So we're just adding a bunch of k states together, where Cn is peaked at some n bar and then tails off. All right, good. So here's where I'm going to set the size of the well. Did I evaluate this? Let's make sure I evaluate that. And so I'm going to start with a equals 1, and we're going to plot the wave function. I'll plot 100,000 points inside the well. All right. Okay. And here's where we actually just make the plots. All right. My sigma factor, the way I make sigma k is I take some constant and divide it by sigma factor. And so this is just making it equal to that 1/2 that we said. And I'm going to execute this and plot it. So here is, can I make this smaller? How can I? Okay, I wanted to make this smaller. Where do I have a zoom? Okay, I won't waste time with this. Oh, shoot. I went backwards, not forwards. Let's get this thing out of the... All right, anyways, we'll live with this. So here's the wave function. It is that sinusoidal oscillation. Here's the edge of the well on the left. Here's the edge of the well on the right. There's some dashed lines there marking the edge of the well. And so the wave function goes to 0 at those edges, and then it oscillates. I chose n bar to be 5, and that's why we have 1, 2, 3, 4, 5, 6 zeros. If I chose 7, we would get 8 zeros, and so on. Okay, I can also plot this is just the square of the wave function. So it's just that squared. And then these are the K values that are contributing to that wave function. And there's only one. There's a point over here, but it's at 0. So we're only contributing that one main mode. All right. So that's not a wave packet. That's just a single stationary state. To make a wave packet, what I'm going to do is I'm going to increase the size of the well. And the way I'm going to increase the size of the well is I'm just going to go back over here and I'm going to take A and set it equal to 2. Okay, when I set it equal to 2, now my wave function looks a little different. This is getting to be more wave packet-like. It still satisfies the boundary conditions, of course. It still goes to 0, but now we have some more peaky stuff near the center. Okay, if I go and look at the K states that are contributing, there's 2 of them. There's these other ones, they're both 0. And so this linear combination of 2 pure sine waves is already giving us a packet-like behavior. And so all I'm going to do is I'm going to keep increasing the size of our well. And so let's go to 4. And so now we see that we've got a packet that is starting to get more and more sharply peaked near the center. And we still have just the 2 modes contributing. So we need to make a bigger change. So I'll make a more aggressive change here. Let's go to 40. So I'll increase it by a factor of 10. And now, what is our wave packet? There we go. So there's our wave packet. It's always been centered on 20 here. What we're doing is we're the center of the well. All we're doing is we're increasing the size of this well. And so it's a bit deceptive because the range of X values keeps increasing. But anyways, the idea is that we're getting this packet like a pulse-like shape. And that is what represents our free particle states. It's the superposition. And so here's psi squared. And now here's our C values, or the phi that we wrote down in Griffith's notation. And this is starting to take that Gaussian shape. And now we can see there's maybe a dozen modes or something that are contributing. Let me make one more change here. I'm going to go to 400. And we should get a very narrow packet sitting inside of a big well. And so there it is. There's our wave packet. And our CN values. Remember we said as we make the well bigger and bigger, our CN function becomes a continuous function of K. And so there it is, continuous Gaussian profile. Let me show you one more thing. I'm going to go back to, this is what I want to show you is a general property of all Fourier transforms, not just the ones for quantum mechanics, for the free particle. So I've gone back to A equals 40. There's our wave packet. And there's our phi of K. And so they both have some characteristic width. What I'm going to do is I'm going to change the width of 1. Remember, I chose the sigma K value to be 1/2. I'm going to, let's say I shrink that K. So sigma K, I'm going to try to make this get narrower. So let's see what happens if I do that. So I set sigma K right here. Sigma K is something divided by some factor. So if I make this factor bigger, I'm going to shrink the distribution of K values. So I'm going to make it 3 times bigger. And when I execute this, what I hope we're going to find is that my wave packet got broad and my range of k values got narrow. If you think about this, this is really showing us the Heisenberg uncertainty principle. K is momentum. So if I shrink the width of my k values that are allowed, I'm saying I know better. I have a better idea of what the actual definite momentum of my particle was. But if I know momentum better, then I know position less, and my wave packet spreads out. And so that is a general feature of all Fourier transforms for classical systems and quantum systems, but it's also related directly to the Heisenberg uncertainty principle. Of course, we could go the other way, and this is the last thing I'll show you. I could, instead of making the width of k values get smaller, I could increase it. So we started at 10. I'm going to divide by 3 this time. And so I should have a wide range of k values. That means there's lots of spread in the momentum. There's big uncertainty in the momentum. That should correspond to less uncertainty in the position. And so my wave packet in real space should get narrow. So let's see what happens. Okay, so there it is. So there's my narrow wave packet, and we should see a broader range of k values. This is like our phi of k that we would get by taking the Fourier transform of our wave function. Okay, good. So those are the things that I wanted to show you. Next time, we'll start talking about, it must be section 2.5, which is going to be delta function kind of potential. So it's kind of nice that we talked about the delta function today. And then that will allow us to talk about finite square wells and scattering from potentials and things like, what's it called? Like penetrating into forbidden regions, tunneling. And so we'll talk about all those things starting, I guess, next week. All right. Thanks, everyone.